held in connection with our anniversary celebrations of UL Space Club webinar series. So let me announce the winners with the poster designed by UL Space Club team. So let me present my screen.
Should I remove my screen, my presentation?
Is it okay for Shell sir? What should I do?
Okay, it's okay. Thank you, Varun. I think it's 3 p.m. now. It's let's start.
Shell sir, can I present my screen for 1 minute?
Okay. Thank you. Okay, you can do that.
Then I will stop sharing. Yes. Now you can present.
Thank you, man. Thank you, man.
Varun. Yeah.
So is my screen is visible?
Yes, Varun. Yes, Varun. It's very clear.
So they are the winners of our webinar's anniversary celebrations quiz. First prize goes to Sandra K from a 9th standard student of BEM Girls HSS Kozhikode, and second prize goes to Eldosam Varghese, who is 11th standard student of GVHSS Madapalli Vadagara, and the third prize goes to Aravind V, who is 11th standard students again from NSS HSS Kunnamdana. They are the winners of our webinar anniversary quiz. And one more thing I just want to share with you, one more good news to share with all the followers and members of UL Space Club is we are going to celebrate the Moon Day, the upcoming Moon Day of 2021 with two programs, two competitions for school students. And we would like to announce our Moon Day program today. So let me make a presentation on that. So is it visible? Hello,
yes,
sir.
Varun, go ahead.
Okay, sir. Our Moon Day program of 2021 is named as Chandra 2K21. There will be two competitions for school students, and the registration will be live from 20 June 2021. And the program will be conducted on 20 and 21 of July 2021. The first competition is Amateur 2021. It will be an astrophotography contest, which will be conducted on 20th July 2021. And another program is Ignited Minds Debate Contest. There will be a debate on the topic privatization of space, challenges and opportunities. Students from 8th standard to 12th standard can participate in the event. And all programs are conducted by the UL Space Club team, and our decision will be final regarding the valuation and other things of our program. So all of you can register for this event from June 20. So all of you are welcome to our program. So that's about it. This year also we are going to celebrate our Moon Day program with it will be a national level competition. So all of you are welcome to that program also. Once again, I would like to hand over the mic to Sriram for giving a small introduction to our program. So Sriram.
Okay, right. Am I audible?
Yes, you are audible.
Oh, a warm good afternoon to all after an interim of half month or so. Thanks to Varnatan for providing the instructions. I cordially invite all the veteran scientists, teachers, UL Space Club organizers, students, and all other participants to the 37th session of UL Space Club webinar series. We, the UL Space Club, is a foundation under the umbrella of Uralangal Labour Cooperative Society, stands for enriching and flourishing the scientific aptitude of students, especially in space field. Within a short time span of 3 years, we conducted many great offline events before the COVID. And exactly in May 2020, in the context of the pandemic era, we began this new journey called the webinar series. And it's going incredibly well for the past 1 year. Today, we took some time extra, which is unusual but clearly purposeful. So I'll make my introduction comprehensive and brief. With that being said, let me move to the official obligations which has assigned to me. Today, in the 37th session, we have Mrs. Krishna Priya Ganesan as the lead speaker on the topic Solid Cells and Arrays, an overview. Couple of weeks ago, I saw an article on BBC hallmarked as the solar disk that could power Earth. Space-based power stations are turning from an ideal dream into a serious engineering prospect, as scientists hope they can take renewable energy into orbit. I know it sounds like science fiction, giant solar power stations floating in space that beam down enormous amounts of energy to Earth. And for a long time, the concept, first developed by the Russian scientist Konstantin Tushkovsky in the 1920s, was mainly an inspiration for writers, actually. Even in 2017, the researchers at the California Institute of Technology outlined designs for a modular power station consisting of thousands of ultralight solar cell tiles. We use solar cells and arrays as an energy source in many satellites even now. We have to know the details and we have to think beyond the current constraints. And we have an expert in all these matters who is currently working as the head of solar panel division at URC in Bangalore with us to cover all matters related to this topic. It's our privilege to have you here, ma'am. I'm gladly welcome you to the 37th session. Welcome, ma'am. And after that, we have all core team members of webinar committee here to give you the instructions when it's necessary. And our moderator is, as usual, Shajil sir, the one who controlling and developing our platform in each and every session. And he will gonna introduce our respected speaker. Our chief mentor, Ikke Kutti sir, the former director of ISRO, who is the backbone of the whole activities of Space Club, is here with us. The whole webinar family, including the eminent scientists all over India, will be with us in this session too. UL Space Club member Navaneet Shajil will handle the Q&A session after the talk. The one who plays a major role in connecting us to UL, Damodaran sir, is here to express the vote of thanks after the session. And Space Club member Nirubama is also there. Right now, this webinar is recording and streaming in YouTube by our member Adil Krishna. All set, good to go. So without any further delays, I invite the moderator Shajil sir to take over the session. Welcome, sir.
Good afternoon to all. Thank you, Sriram, for making such a good environment to receive this today's wonderful talk from an eminent scientist from ISRO. And we have been sitting for 1 year here during the pandemic. And even though the world is suffering with these kind of miseries, the students really enjoying it in a good way. Taking it is everywhere we find an opportunity to explore these areas and develop for development. That's why we selected this platform, and we are continuously having more than 100 students to follow these things for 1 year. That's a wonder, and that's only because of the environment through which our students are growing. That is being reflected during their, or that's reflects in the other activities, and actually they are the designers and executors of this program. We elders are only the supporting thing for this great event. That is the major part, major significant part of this program. That's a unique system we could arise, and we are developing here. Anyhow, today we have a good speaker from UR Rao Satellite Center, Bangalore. And formerly we had 2 sessions on spacecraft mechanisms and orbit dynamics from the same institution. Mr. N.S. Murali and Mr. Subramanian B. were the 2 speakers. We received the talk from these great institutions. We know it's a institution where the national secrecy is most influenced or most considered. So it's very difficult to get such a speakers from these institutions. But recognizing our motive of this UL Space Club, and it is well convinced by our founder Ikke Kutti sir, to this organization, we could get these eminent speakers and scientists from UR Satellite Center and other institutes under our prestigious organization, ISRO. So today we have the the chief guest here, Madam, and she became part of this ISRO in 1997, and now she is the head of Solar Panel Division, URL Satellite Center. We know energy is the main source for working even the life and the non-living mechanisms in this world. So there is the main source of energy in this universe is the sun, and we are capturing that energy and we are utilizing it for our benefits. So that's a great practice and dedication, and a lot of innovations are required there. And we are in search of such innovations in our country to contribute in all fields of our science. So ISRO is also doing a good job in for the self-reliance in this case of energy in satellite managing systems. The madam here we have, she is is working as a head of this project and supporting our great organizations. And along with that, we can proudly say that by hearing and experiencing these kind of scientists and their exposure to this environment, our students are get motivated, and now they are even thinking about making a satellites. There is a team under Varun is designing such a things in black and white, and they are going to execute it. That's only because of the environment. That means the personality is equal to G square, genetics is there, but the environment is a square area is there. That's a great influence of environment that we are creating here, and we can proudly say that we are doing that. And we are publishing and make the other people of this world all other activities through our website, ulspaceclub.in. And we are proudly presenting that website also that already launched here. And along with that, we launched one Stellar Chronicle, that is an e-magazine. That's also that also reflects the creativity of our students in these occasions. So without taking any more time, I invite all the veteran scientists and students, teachers, and all other community who are watching this program globally. That's also a proud to us. And I invite Krishna Priya Madam to present her wonderful presentation. Welcome, ma'am.
Thank you, Shadil sir, for this nice introduction. So I will share my presentation now. Shall I remove the video? I will remove the video so that the presentation can go in smoothly. So good afternoon, everybody. I really thank UL Space Lab to give this opportunity to present the webinar Solar Cells and Arrays to such a august audience. Without much introduction, I would like to go into the presentation. So as I was introduced, I am Krishna Ganesan, and I am heading the Solar Panel Division in URL Satellite Center. And we are responsible for realizing the solar arrays for the ISRO missions that are launched. So this is the brief agenda which I will be covering today. And anytime anybody has any doubt, you can please interrupt me, or you can consolidate all your doubts and ask me after this webinar. As planned, I will be covering around 1 hour 15 minutes, and I will try to go fast in some basic portions also that we have tried to cover, because I was not sure what the age group of the audience. Initially, I started preparing for +1, +2 level, and subsequently I came to know that people from 8th standard is getting involved. So I have tried to introduce some basics also. So the seniors may feel it boring, but still it is worthwhile. So before going into the details, why a solar cell? Why so much of interest is there on solar cells for quite some time? This is because the energy demand by the world is increasing like anything. And presently, around 85% of our energy demands are met by non-renewable energy sources. So, non-renewable energy sources are mainly fossil fuel, coal, natural gas, and nuclear. These four entities, they are right now supporting nearly 90% of the energy requirement. And if we remove nuclear, these three are supporting 85% of the requirement. So these fossil fuel, they are coming to an end. Like we know that we are about to deplete the amount of energy that is available for us from Mother Earth. Another reason for uh, looking for other alternatives is this usage of these non-renewable energy sources. They are causing what is now known as global warming. Global warming is slowly making our Earth non-livable. Now, another reason is the toxics which are getting released due to the usage of these non-renewables. So what is the other solution? We have to move towards renewable like wind, geothermal, hydroelectric, and solar. And solar is attracting very good interest mainly because the amount of sunlight that we receive probably in 1 hour is more than what is our global demand for 1 year. So such an abundant source of energy is available for us to use and for us to explore. That is the main reason for many experiments and research going on in renewable energy and especially in solar. It is also a very clean energy, and we can very well minimize the losses because we can install solar array wherever the users are. There are no line drops, line losses and all, and it's very reliable. The present solar array technology is so reliable that we can install some solar system for say 20 years and it will keep giving us power. So these are the reasons why a solar cell is attracting so much of interest in the present context. Now coming to what is a solar cell. So we can define solar cell as a two-terminal device. It's an electronic device. So it converts, the basic principle is any electronic that converts light energy into electrical energy can be called as a solar cell. Also, it uses solar spectrum, it is renewable. There are no moving parts, so there is no wear and tear. It has a long life, and as I told, it's a very reliable performance. In this context, I presently selected this picture because I wanted to give a tribute to the trees which are in the earth. They are giving us food, they are giving us oxygen to breathe, and they are doing what our solar cells are doing from historically many years. They have been silently making use of the sunlight and also giving us the required food and oxygen for millions of years. So that's a tribute to the trees that we see around, and we have to really respect those trees. That is the message I want to give as part of this webinar. So coming to history, I will slightly go into history of photovoltaic and photoelectric effect for the young audience because without this going into the deeper subject will not make any sense. So this effect of Becquerel effect was observed by Edmund Becquerel in 1839. It was observed by him that when a platinum rod coated with silver chloride or silver bromide, when it was exposed to sunlight, it resulted in generation of voltage and current. This was observed and recorded, and it was named as Becquerel effect at the time, but it was not explained. And subsequently, in 1887, similar observation was made by Heinrich Hertz. When light is falling on a metal surface, electrons are ejected out of it. And at that time, the prevalent theory about light was Huygens wave theory. And with wave theory, these observations could not be explained. Either photoelectric effect or photovoltaic effect could not be explained using Huygens wave theory. And since most of these people like Hertz and others who were working these phenomena, they were all supportive of this wave theory. They could not go beyond the wave nature and explain these observations. So in 1902, Albert Einstein gave a very good explanation for photoelectric effect based on the particle nature of light, which was proposed by Max Planck. So he explained that if energy of the incident light E, and he also explained that the energy is related to the frequency of the incident light by E is equal to h nu, where h is the Planck's constant. So he explained that if the light of energy E is falling on a metal surface and some electrons of energy E is getting knocked off from the metal surface, this relation holds good, where the kinetic energy of the knocked off electron is equal to the difference between the incident energy and the work function, where work function is the minimum energy required to knock off electrons from a metal. So he also explained that the incident intensity is directly proportional to the number of electrons coming out of the system. And if we increase the frequency of the incident light, the kinetic energy of the electrons are increasing. So this kind of relation or this kind of explanation can easily be provided to explain the photovoltaic effect that was observed by Becquerel earlier. In photovoltaic process, electrons are not ejected out of the material, but it is moved from one state to another state, which enables conduction in this material. Now we will just understand the energy band to explain things which are coming further. Assume there is a nucleus which is having an electron in one of its orbit. There is another orbit outside it which is empty. So we can denote these two energy states E1 and E2, which can be occupied by the electron. So this electron has only two states, E1 or E2, and in between whatever energy is there, that is forbidden, or it cannot occupy those energy states. Assume two atoms are coming together. This band, this single line becomes a small spread is there because two atoms, two states are there. Similarly, if you take a crystal, there are many electrons, many atoms available, and they form E1 is becoming a band and E2 is also becoming a band. These two bands are called the valence and the conduction band, where valence band is the occupied band and conduction band is the unoccupied band. So now if we see there is a band here in the picture in the right, there is a band here which is occupied by electrons, and there is a band above it which is at a distance of Eg, or which is energy gap of Eg, which is empty at 0 Kelvin. And if you go to normal temperature, which is more than 0 Kelvin, we see that some of the electrons are jumping to this by taking the energy and occupying some states. So this kind of band structure is what is finally causing the conduction. So at 0 Kelvin, this is not able to conduct because there is no electrons available here, whereas here electrons are available in the conduction band. Now I will just explain how material are classified into based on their conductivity. They are classified into metals, semiconductors, and insulators, because metals in which valence band and conduction band, they either are very close or they are nearly overlapping. So even at room temperature, some electrons, they just leave the valence band and they can occupy conduction band. That is why metals we have seen it is having a very good conductivity. There are some other material where the valence band and conduction band, they are separated by a few electron volt of energy gap, say 3 electron volt or less. And there are some other material where the band gap or the energy gap is more than 3 electron volt. In the last category of material, even at the room temperature, there are no electrons possible in the conduction band. There are no electrons available. So they do not conduct electricity and hence they are called insulators. Now coming to the middle category, where this is a these are called semiconductors because at 0 Kelvin they act as insulators, but as the temperature increases and probably even at room temperature, a few electrons in the valence band can go to the conduction band and hence they are, they are having a small degree of conductivity. So these semiconductors, if we see the periodic table, they occupy whatever is written in blue. These are all the elements that can show the semiconductor behavior, and we can see most of them are having covalent bonding to each other, that kind of a chemical behavior. Now we will try to understand what is the meaning of intrinsic and doped semiconductors. So we have taken a silicon crystal. A silicon crystal is having four electrons in its outermost shell or valence shell, whereas it will get satisfied if there are 8 electrons in its valence shell. So in the crystal, it is sharing 4 electrons from its neighboring silicon atoms, and finally it is satisfying its 8 valence electrons by forming covalent bonds. In this condition, the silicon crystal is not showing any conductivity because all its electrons are bound in its valence electron. Now assume that I am trying to dope this silicon crystal with some other material like a trivalent or pentavalent impurities. Assume one pentavalent this antimony. This is occupying the silicon lattice in one of the lattice locations, and for antimony there are 5 valence electrons. So 4 are used to share with its neighboring silicon, and 1 electron is available very loosely bound to this atom. So when I dope this silicon crystal with a pentavalent atom, it has so many donor or free electrons available. So it is called a donor impurity, and the material becomes N-type doped semiconductor. Similarly, if I try to dope this semiconductor with boron, which is a trivalent atom, there are 3 electrons that are shared with the neighboring silicon silicon atoms, but there is one vacancy. For this particular area, there is no electron which this bismuth can give. So this acts as a hole, and if another electron from a neighboring atom comes and occupies this, the hole moves there. So in p-type material, the conductivity happens, but it happens near the valence band because an electron jumping from one hole to another hole or creating or leaving a hole behind, that is the mode of conductivity. So if we see the band gap of these materials, in intrinsic, the Fermi level or the Fermi level of this intrinsic band, what is the Fermi level? That is the maximum energy that can be occupied by an electron at 0 Kelvin. So the Fermi level is between the valence and conduction band. In the N-type material, the Fermi level moves near the conduction band because many electrons are able to have energy level which is near the conduction band. Whereas in a p-type material, the Fermi level moves near the valence band. Now assume we are going to make a PN junction, which is nothing but a diode. We are trying to make a diode. So an N-type material and a p-type material, which is having a band structure, we are trying to fuse them together. So what happens? There are so many free electrons in the N-type region, and there are holes available here. So these free electrons, they try to diffuse to the p region and try to occupy the holes. In this diffusion, they leave so many atoms behind, which is positively charged. So there is a charge which is building up in the interface due to the movement of charge carriers or electrons from N region to P region. The N region becomes positively charged and the P region gets more and more negatively charged as more and more electrons diffuse to this through this area. So as a result, there is an electric field or a space charge happening inside the area, which this area we call as the junction, correct? So near the junction, there is an electric field which is developed, and this area is devoid of any free charge carriers, because whatever free electrons were there, they have already moved here and occupied these holes. If some more electrons want to cross this junction and come and occupy the holes here, it is not able to do so because of this electric field, because the electric field is pushing the electrons towards this direction. And if we see the band structure has bent in order to keep the Fermi level stable. Our Fermi level within the material has to be aligned, so the band has bent, which results a minority carrier in the P region sees a slide and it will try to move to the N region. Similarly, a minority carrier in the N region or a hole, if it is created, it will see a slide and it will move towards the P region. So if this kind of a material, I make two electrodes and try to illuminate with light, what happens? So with the photon incident on the junction, one of the electrons is kicked out of this valence band and it moves into the conduction band. The electron which is moving the conduction band sees a slide, and the hole is getting attracted to the other side. It is repelled by this electric field and it gets collected by the metal, which is the electrodes. So this is the mode of functioning of a solar cell. So here in solar cell, three major activities has to happen. One is the carrier generation, or electron hole pair generation has to happen. The second activity is carrier needs to separate and the carrier needs to get collected. If these three activities happen, this particular interface can act like a solar cell. So now coming to the previous equation, if E is the incident energy, which is equal to Hf, if F is the frequency, we can also write it as hc by lambda, where c is the velocity of light and lambda is the incident wavelength. So if we move this lambda here, E into lambda is equal to a constant, which is 1240 electron volt into nanometer. This is a unit. So this is a constant. Based on the incident wavelength and the energy gap, we can know if this particular energy will be absorbed by this material or not. Any energy which is lower than this lambda will be absorbed, because it can take that energy and go from the valence band to conduction band. But beyond a particular wavelength, it will not be able to absorb because it cannot cross the energy gap. That kind of a wavelength is called the cutoff wavelength. So for silicon material, or for silicon diode, which is having a band gap of 1.12 electron volt, the cutoff wavelength is 1100 nanometer. And for gallium arsenide, which is having an energy gap of 1.42 electron volt, the cutoff wavelength is 900 nanometers. So we know why certain frequencies are not absorbed by the solar cells when its energy is insufficient to pick off electron and push it to the conduction band. Now this is, I will go a little bit fast because these are all just equations. I will leave the presentation with you. So here it is a very preliminary way of that is writing the diode equation and explaining how the solar cell functions. The current coming out of the solar cell is then the light generated current minus the diode current minus the current which is getting dropped by the shunt resistance and which is dropped by the series resistance. That is the basic solar cell equation. We also see that here you see this is nothing but a dark diode forward characteristics. This is the reverse area and this is the forward characteristics of a dark diode. If this diode is illuminated by light, the light generated current will push the characteristics towards the fourth quadrant, and this forms the IV curve. Whereas in a solar cell, the diode is not forward biased. Since the space charge is there, it is generating a potential by itself, and hence we move it to the first quadrant, and this is the IV characteristics of the solar cell, and we have defined some points here. One is the ISC or the short circuit current, VOC or the open circuit voltage, Imax and Vmax, which is the maximum power point current and voltages. And these are the other definitions which you can see later. And now you see how the power that is coming out of the solar cell varies. This is the current voltage graph, and this is the voltage versus power. Am I audible?
Yes, ma'am.
Okay.
Yes, you are, madam. You are very much audible.
Okay. So this is the power versus voltage graph. So you can see that the power increases as we move from ISC towards the VOC. The power increases from the solar cell, and as we cross the knee region, the maximum power is obtained from the solar cell. So this point at which the maximum power is obtained is called the maximum power point, and the corresponding current and voltages are called IMP and VMP. Now we see how the solar cell characteristics changes with temperature. So this is the IV characteristics at a very cold temperature, and as the temperature increases, we can see that the shape of the IV changes. The current drastically reduces as the temperature increases, but the voltage marginally increases. So at a higher temperature, the current will be marginally higher and the voltage will be drastically lower than the IV characteristics at a lower temperature. And if we see the incident illumination versus the IV, as the illumination or the sunlight that is falling on the cell changes, the current proportionally increases or decreases. Like if the light is increased, the current that is coming out of the cell is increased. Whereas the voltage will change logarithmically. So if the illumination is decreased, the VOC decreases logarithmically, or if it is increased, it increases logarithmically. So this is the relation of IV curve with temperature and illumination. Now we come to what is known as the solar spectrum. To understand the functioning of the solar cell, since we are working in both terrestrial as well as in space regime, we should know how the solar spectrum is defined. So here you can see the, I will explain this and go further. Here you can see the sun in two different orientations. Mean sun-earth distance, if the sunlight travels through zero air mass, or if the sunlight which is received at mean sun-earth distance without traveling through the atmosphere, that spectrum is called air mass zero or AM0. And the sunlight which is received normally at Earth's surface at sea level is called air mass 1. For our terrestrial purposes, we define a term called air mass 1.5, which is at an angle of 48.2 degrees from the normal incident sun. So the difference between what we use in space regime and what we use in terrestrial regime is AM0 versus AM1.5. The energy that we receive in AM0, if we integrate the energy below this graph, we get 1353 watts per meter square, whereas the AM 1.5, which is at an angle of 48 degrees from the normal sun, we get around 1000 watts per meter square. So that is the difference of sunlight that we receive at space and at Earth. Now you can see the sunlight has a very vast spectrum. It starts from around 0.25 microns or 250 microns, 250 nanometer, and it extends up to more than 3000 nanometers. and the red graph is AM0 and the green one is the AM1.5. The green one is markedly different from the red graph because this portion in the UV or whatever is between 250 and 400 microns, it is absorbed by the ozone layer, and it is a very small amount of UV reaches Earth. Whereas the visible light, which is from 400 to say 780 nanometers, this is markedly lower because of the scattering and other absorptions happening in the atmosphere. In the IR region, we can see many troughs. These are due to the absorption by many atmospheric content like carbon dioxide and water vapor, and you see that a lower amount of light is reaching the Earth. The spectrum itself is divided into three regions: UV, visible, and IR. So these are the standards that we use in the solar array industry for as a reference for the sunlight. Now coming to the different generation of solar cells. This graph will be very confusing, but it is very useful graph. This is the graph recorded by National Non-Renewable Energy Lab, which is in USA, which is tracking the solar cell research and the recorded efficiencies. So the y-axis is efficiency and x-axis is time, as you can see. And there are multiple lines which is going. I will mainly talk about the three separate generations that is here. The purple and the blue ones, they constitute the first generation. The green one, they constitute the second generation, and the red one, the red graph which is far below, that denotes the third generation of solar cells. Now, to understand what is first, second, and third generation, we will go through some more details. So, the first generation of solar cells started with silicon technology in the year 1957 when Bell Lab they reported their first solar cell with monocrystalline silicon. So the first generation uses traditional methods. They go with solid state cells, that is very thick and very heavy cells. And we can categorize the traditional silicon, which is monocrystalline and polycrystalline silicon, the gallium arsenide technology, and the germanium technology. These are the technologies that we presently use in the space industry. All technologies we can categorize as first generation. These cells are extremely expensive. These are made with, they are extremely expensive due to the following reasons. One is they use very high purity material, and they also use expensive machinery and very, very costly processes. So these the things push their cost to a very high level, but they have also achieved very high efficiency. The last reported lab level efficiency is more than 47%. But in this, we can consider the silicon technology, which is monocrystalline and polycrystalline. They are very popular in terrestrial solar array, whereas the gallium arsenide based and germanium based solar cells, they are very prevalent in space industry. Now coming to second generation. The second generation of solar cells, they started to bring down the cost. So the main idea of second generation was to use thin films so that the bulk material is not used as in the first generation. And the prominent technologies that we see in the second generation is, one is amorphous silicon, another one is CIGS technology, which is copper indium gallium selenide technology, and cadmium telluride modules. They are mainly thin films, as I told. They also use very costly input material, but they have tried to reduce the cost by controlling the processing as well as the amount of material that is being used. They are fairly stable. They are not as reliable as the first generation solar cells. They are fairly stable, and they have achieved a fairly low efficiency of around 23% now. But since they have started late, they have now reached here. Most probably, they will also achieve very high efficiencies with the kind of research that is happening. For the last 20-30 years, the third generation of solar cells is creating explosive research and say products in the industry. The areas that are covered under third generation can be categorized like organic solar cells, dye-sensitized solar cells, perovskites, hybrid composite solar cells. Everything can be combined as third generation solar cells. They started very late. In the 90s only they started, but the kind of sophistication they have tried to apply and reach very good efficiency, that is phenomenal. So here they use the engineered material, new type of material, nano material, and nano technologies to get very good interfaces. So this has resulted in what we can now tell as very low cost as well as easy processing and very cheap processing. These cells can be processed like screen printing or say tape coating. Like that, processings are so simplified. But the issue with these cells is they have in-shelf as well as light stability issues. They tend to degrade once they start getting used. So those things have to be addressed. But this is one of the very promising generation of cells, and I'm sure this will overtake the generation 2 and nearly reach the generation 1 solar cells in a few years from now. Now coming to multi-junction solar cells, these are the solar cells that we use now for our space application. The advantage of multi-junction solar cell is it has a very high voltage as well as very high efficiency. Right now, whatever cells we are using, it has an efficiency of around 30%. So, what are multi-junction solar cells? So, multi-junction solar cells are nothing but cells stacked over one another. So, how the stacking over one another helps? It helps in such a way that the full solar cell spectrum is used effectively. So, here I have shown the AM0 spectrum. We are having three solar cells in this picture below. So the top cell is gallium indium phosphide, the middle cell is gallium arsenide, and the bottom cell is germanium. The band gap of top cell is around 1.86 electron volt. The gallium arsenide has a band gap of 1.42, and germanium has a band gap of 0.66. Since the band gap is very high, all the energy or the blue marked region of the sun spectrum can be utilized by this gallium indium phosphide. It cannot use all these spectrum, which is beyond around 600 nanometer. So it absorbs this part of the spectrum, remaining light goes inside to the next side. Since gallium arsenide has a cutoff wavelength of around 880 nanometer, it uses this small red marked portion, and the remaining energy is sent to germanium for its conversion. So here the cells are matched and lattice matched, and even the usability of the spectrum is so matched that we are getting a very high efficiency from this kind of cell. So multi-junction cells are nothing but tandem cells which are lattice matched. So here, this is there as I write here. This is the zinc blend structure. They have the zinc blend structure, and they have to be lattice matched, and they have to be grown one above the other. So the top cell or the gallium indium phosphide cell IV characteristics is like this. The middle cell gallium arsenide cell gives an IV like green one, and the red one or the germanium cell has an IV characteristics, and they are current matched and form this gray one, which is the total IV curve of the gallium arsenide cell, the multi-junction cell. So now coming to terrestrial solar cells and solar arrays. Okay, I have already.
Ma'am, Farhana here. Can I ask a question,
Yes,
ma'am?
Farhana. Yes, Farhana.
Ma'am, I just went through some literature, and they have seen that when they have migrated to higher bus voltages of nearly 100 volts or so, some solar array fogging was observed in case of Boeing bus, and they are telling they have resolved it by the usage of triple junction cells. So, can you just throw some light on solar array fogging issue and how it is resolved with the usage of triple junction?
I'm not sure about the fogging because one is the outgassing which happens in the solar array.
Okay.
I'm not aware of this observation. And anyway,
Yeah. Priya madam, hello.
Yes.
This Dr. Reddy madam. I think Farhana madam is telling about the torquing madam, and we go for higher voltage, higher bus voltages.
Okay, I will
Plasma.
explain
Plasma.
about
I
the
think
arcing
she's
later.
telling about plasma.
Arcing.
I will explain in the following slides. It is not fogging, it's arcing. Okay, I will come to that.
Okay, ma'am.
And Farhan, I have tried to keep this presentation as generic as possible. I am not concentrated on the space because other kids are also there. For students, we have to keep it attractive. I will anyway come to arcing when we come to the space solar arrays.
Fine, madam. Thank you.
Okay. So coming to terrestrial solar cells, what are the main factors we have to consider when we are designing a terrestrial solar cell as well as a solar array? So here we see that the cell has to work in the AM 1.5 spectrum, or which is in the terrestrial sunlight. Another main thing which we can see from the market is 93% of the market is being populated with either single crystalline silicon, polycrystalline silicon, or amorphous silicon. So still the first generation and the second generation, these cells still dominate the market. The other cells which are seen are a little bit of cadmium telluride. The third generation has to catch up. It has not yet caught up with the terrestrial market, but with the present kind of products which are coming out, it is not too far away in the future that we see some windows with solar cells or some vehicle top steps sprayed with solar cells. It is very well in the future. Another thing which we have to attack is the cost effectiveness. So we usually compare what is our grid cost. Whatever grid we see, what is the amount we spend per unit power. That has to be matched to attract the customers and the customer market. The fourth point which we have to certainly address is we cannot have a degrading solar array. It has to have a very good reliability, so that we install the solar say farms, and it gives us very good power for at least for 20 years. It should give us a very good power. Another factor is ease of production, so that large scale production is possible, and it should also pass all the testing which is specified by our Indian government. All these Indian standards it has to match. And another difference which we see comparing the space cell and the terrestrial solar cell is these terrestrial modules have to be hermetically sealed. This is to ensure that with the available humidity and oxygen environment and at high temperature, the metal parts in the solar array as well as the cell itself does not degrade or does not get tarnished, which is very much possible in the earth conditions. The terrestrial modules are also being made in modular units, so that replaceability and repairability is also possible. On the right side, I have just indicated the stages by which the terrestrial solar array is being made. Like initially the ingot is cut, it makes a wafer. The wafer gets diffused, and the PN junction is made, metallized, wired to connect them in series and parallel. It gets glassed to get or get mounted in a glass to give the mechanical support. Then subsequently it is protected with the film and encapsulated. Then handles are fixed, and these are the modules that we get in the terrestrial photovoltaic array. Now coming to what are all the types of installation that we see around. First one is the solar farms. You would have heard that this company or that company has installed, say, gigawatt range of power. That is being done with thousands of solar modules, terrestrial solar modules installed in barren lands. So this can be connected to the grid for generation of power. So this will be a DC power, and through grid it will be converted to a AC using an inverter, and it can be transferred to the user using grid system. Another system which is picking up nowadays is floating solar form. So in this process, some water bodies are selected in which floating mechanisms are installed, and the solar array is installed in that floating mechanism. The advantage of this system is inherent cooling of the solar array module happens as the water cooled, and in some cases even air cooled systems are also possible. By keeping the array temperature to a lower level, the array efficiency can be improved. The third kind of solar installations that we see in our surroundings is our rooftop solar. This is a very good system being uh, encouraged by the government to ensure that households and institutions, they are covered by, they invest and install the solar to ensure that power generation happens in small units also. The fourth one, the concentrated PV, is a very ambitious mission. Here I will tell the difference between these other three installations and the concentrated PV. In other three installations, we used it normal cells of silicon or polycrystalline silicon or other technology, whereas in concentrated PV, the technology used is the multi-junction solar cells. Since multi-junction solar cells are extremely costly, we cannot install such big solar arrays and generate power, because it will be very not cost viable. Cost wise, it is very expensive. So a small multi-junction solar cell is placed at the tip of this tripod. You can see this kind of tripod. Maybe the solar cell may be of size 1 millimeter by 1 millimeter, and this huge reflector, which is an optical grid reflector, that is used to concentrate the sunlight to this tip of, it is at the focal point of this grid, and the light is focused here, so that a small solar cell, it receives, say, 500 times or 1000 times the solar sunlight, which is 1000 times the illumination. So with a small solar cell, we will be able to generate a huge power. But this has not picked up so far because of the factor that the thermal management of this small solar cell, it becomes very critical. It has to be uh, actively cooled by using many mechanism, as well as the design of this optics. This optics has to continuously track the sun. For that particular latitude and longitude, we have to know how the sun moves, and it has to track in such a way that the light is properly focused in this solar cell. But research is going on, and probably in future we will see many more installations other than the pilot installations which are available in the world presently. So now we move to the space solar cells. I will briefly talk about the considerations that go into the space solar cells, and what are all the criticalities that we have to see for space. Those things we will cover in the following few slides. So coming to the space solar cells, as I told you, they are designed for a sun solar spectrum, which is called the outside atmosphere, or which is the AM0 spectrum. So the three junctions are matched in such a way that the light, which is very rich in UV, visible, and infrared, can be used by this particular cells. Mainly, we are using multi-junction solar cells presently for the last 20-30 years. But in the 80s, we were using silicons predominantly, and in the early 90s, we were using gallium arsenide cells also. So silicon cells of around 12% was used earlier, and gallium arsenide, when we moved on, the efficiency was around 18%. And presently, we have used the multi-junction cells of efficiency up to 30%. So right now the market is dominated by multi-junction solar cells of say size 4 centimeter by 8 centimeter or 8 centimeter by 8 centimeter. We are being using rigid cells as well as flexible cells are also in the market. These cells are extremely costly and extremely reliable. The reliability comes into picture because in space there is no way of repairability. Once we launch the satellite on the tip of a rocket, we don't have any control. We have to, there is no possibility of retrieving the solar array and repairing it if something happens. So we have to ensure that whatever solar array we make, whatever solar cells or the solar array we make, it functions properly as expected for the life that is designed. That is how it has to be extremely reliable. The extreme high cost of installation. This is because the raw material used, the processes, everything is very complicated, which pushes its cost. And it has to be tested not by the terrestrial test methods. It has to be tested by special methods, which is followed in the space market, either S11 or S12 of AIAS specification or ECSS. This is by the European space and this is by the American market. These cells are custom built, or we can tweak the cell to work in certain specific conditions. Either the size can be changed, or the junction can be changed, or its grid structure can be changed in order to suit our mission. And as I told earlier, we use ultra pure material here. We use very complex processes. We use very expensive machinery and labs. And this particular technology is owned by very few companies worldwide. Actually, 4 companies in the world own this technology. So that also pushes its cost. Now we'll just see why the space is very difficult and what is its impact on the design of solar cell and the solar panel. So the first condition is we should ensure that the solar panel and the solar cells, they are able to sustain the launch vibration and acoustics. As the rocket takes off, it makes so much of mechanical noise, and that noise usually affects the very brittle and very thin and the solar cells, and this can cause cracks and breakages to solar cells. Once the cells crack and its continuity is lost, then it will stop giving us the power. So our arrays and solar cells should be designed in such a way that it survives the launch vibration and acoustics and it does not crack or break. The second condition which we see in space is the UV radiation. Even in ground, we know that the UV attacks the optical properties of different materials like adhesives or optical coatings. They all become darkened when it is exposed to UV. So this can, the UV radiation which is available in space, and the solar cell is going to see the UV light continuously falling on it because it is seeing the AM0 spectrum. This can degrade the optical properties if we do not specifically select good coatings or good materials on the solar cell. So that is another very important aspect which we have to worry about. The third condition is deep vacuum. Once any material is exposed to vacuum, it starts what is known as outgassing. The low volatile material starts coming out from the system, and this low volatile material can cause a very big as Farhana was saying, fogging around the solar panel or the spacecraft, and it can contaminate the spacecraft. This should not happen. So we should ensure that our solar cells and solar panels do not contaminate the spacecraft or the space environment or the our satellite. For that, we select specific materials which are low in outgassing. Or our processors, material, everything is to ensure that they perform as expected in vacuum. Another interesting thing is the temperature cycle. As the solar cell sees the sun, its temperature can go as high as more than 100 degrees Celsius. But as the satellite goes around the Earth, it can go into some places where the Earth's shadow falls on the satellite. During that time, the solar cell will not be able to see the sun, it will not be able to generate, as well as its temperature drops like anything, and it can go as low as minus 180 degree in our geo missions. In our low Earth orbit missions, the temperatures can go as high as 130 degree and minus 100 degrees. This temperature excursion, like once a material is heated and cooled multiple times between these kind of temperatures, it can cause failures in the interfaces. So our choice of material and process we should select in such a way that this kind of excursions also it is able to sustain or successfully pass. Another aspect is the temperature cycle. This is the kind of temperature excursion that we talked about, and this is the number of cycles it has to see throughout its life. Once a satellite is placed in a geostationary orbit for say 15 years, it will see around 1400 cycles throughout its life. Whereas a satellite placed in a lower orbit for say 5 years, it will see around 30,000 cycles in its life. That is 30,000 times it will be heated and cold, it will be exposed to sunlight and put into the darkness. So this many cycles or this kind of temperature expression as well as temperature cycle can cause what is called as fatigue failures, and this can result in delaminations, adhesives can debond, some cuts can happen in metal interfaces. So all these things have to be designed properly. Another very critical thing which we see in space is the particle radiation. The sun has always been throwing out particles like alpha particle or beta particle, electrons or heavy ions. Also, the Earth's magnetic field or our Van Allen belt that has trapped many active particles or charged particles, and these particles are very energized particles, and it can come and hit the solar cells. Once such energized particles, heavy or light particles or ions or electrons, once they enter the solar cell, they can cause damages to the solar cell. And if such damage happens, the solar cell efficiency comes down. So our solar array should be designed to take care of these kind of defects which will happen through its life. As you know, the space is filled with junk particles or micrometeoroids, which are either natural or man-made. And nowadays, the man-made micrometeoroids are so large that there are satellites planned and launched to capture the micrometeoroids so that the satellites or the active our space assets are not damaged with the mechanical damages just because some unknown particle or a small particle comes and hits our satellite. The solar array being exposed outside the satellite, and it's so huge, it will be some meter squares of size. So there is very large probability that some micrometeoroids of a very small particle, say 10 centimeter or smaller particle, can come and hit the solar array. So we have to ensure that our solar array does not fail due to this kind of mechanical impact. This is a very curious observation which happens only in lower missions. You know that the topmost layer of our atmosphere is the ozone. The ozone layer is covering our atmosphere, and as the UV particle hit the ozone layer, ozone gets formed as well as it gets dissociated. The dissociation of ozone causes atomic oxygen species, and they start drifting towards the area which is beyond our atmosphere. So, as some satellites are deployed in low Earth orbits, say from 200 kilometer to say 500 kilometer, we encounter species called atomic oxygen. Atomic oxygen is a very reactive species. It oxidizes whatever surface it gets. So in order to successfully place the or function the satellite for 5 years, we have to protect low Earth orbit solar arrays as well as other exposed surfaces from erosions that can cause due to this atomic oxygen species, and ensure that our surface properties, either optical property or thermal property, they do not degrade due to the reaction due to oxygen. So this also has to be taken care. And now we come to the very critical and very serious problems which satellites have faced in orbit, which is called differential charging or arcing. You would have learned that when some material gets charged, some insulator gets charged, after it crosses some threshold, it will just try to discharge itself and by a small spark or an arc. So this same thing can happen in space also, especially in solar panel, because the solar panel is covered with insulator and it has metals, it has current carrying lines, and as the bus voltage increases, the solar panel is generating more and more voltage. It can get charged. The insulator on the solar array can get charged and try to discharge to the metal parts of the solar array. This has created very serious damages to the solar array because of arcing. This has resulted in power loss of many missions, especially in the early 2000 to 2005 time frame. And we have to design our solar array in such a way that the differential charging, even if it happens, our array is free from arcing. Our array should not cause any arc, due to which our array itself gets damaged. So that kind of design also we have to take. So with all these space environment and its impact, how we are keeping the very thin solar cells or our modules alive for a long time, say 15 years. What is that? We put it into the satellite solar array. So I will now categorize our satellite or the care that we put in the satellite solar array into these 4 categories. These are the quality controls that we
Krishna Priya ma'am.
Yes.
Ma'am, this is Archana. I'm from
Yeah.
Geoscience.
Ma'am,
May I
interrupt? Ma'am, I think the question and answer session we can discuss after this presentation. I think
Okay. No issue.
Okay, sorry, Shajil. These are all our people, so we have a habit of disturbing each other during our discussions.
Okay.
Sorry,
Thank
Shajil.
you. Okay. Thank you, madam.
So I will categorize our quality control into 4 main categories. How we ensure that the solar array that we send up it remains or it meets the quality requirements that is expected out of it. So the first category I will put it as the design. We take so much of conservation in our design, so that we predict, we model, and we predict what is going to happen to our solar array once it is exposed to this kind of very what to say very adverse environment in space. This model will be converted into numbers, and we put so much of margin in the numbers, so that whatever solar array we design and we send up, it is going to see such adverse environment. It is going to degrade, but still it degrades by the number that we predict. That kind of design is put into the system, and we also place some redundancies. Redundancies means we keep 2 systems or multiple systems in place, so that even if one system fails, the other systems are able to take care of the functioning which the failed system has to support. So we build conservative design with many margins and redundancies. This is the first care that we take. The second kind of care that goes into the solar array is the selection of material or the material choice. We select material which are low outgassing. As I told, we do not want to contaminate the satellite of the solar array. The solar array has many material like some are metals, some are insulators, some are semiconductors, and some are composite materials. So all of them have different thermal expansion coefficients. These have to be matched in such a way that when it goes to hot or when it goes to such a cold condition, they do not have any abnormal or imbalanced expansions. That will be addressed by selecting proper material or proper engineered material. Another condition that we take is we have to use many resins and adhesives to bond our systems together. All these resins and adhesives are selected in such a way that their glass transition temperature, or TG we call, the glass transition temperature is extremely low. So if we talk about resins or elastomers, there is a temperature above which the elastomer will have a very good Young's modulus, very high Young's modulus, and it will be very rubbery in nature. But below its glass transition temperature, it becomes like a glass, or it becomes rigid or fragile. So if we select normal adhesives, which are used in terrestrial condition, the cells can crack because as we go to a lower temperature, the glass transition temperature is crossed. So we take care to choose proper material for resins and adhesives. We also select our metals which are having long fatigue life. We also select material which are electrically, mechanically, and thermally superior, radiation tolerant, low weight, and has heritage usage in previous satellites or spacecrafts. So this is the care that we take in choice of material. The third category or the process. This is where as a solar panel division, I can claim that this is where we have so much of our stake. We develop so many processes. We go through so many design of experiments to ensure that the processes meet or exceed the requirements that are required to keep the satellite solar array intact in the required mission as well as beyond the mission. Any process that we choose that will go through a detailed design of experiments, we fix the parameters, whatever the variable parameters we select, because thousands of cells are getting incorporated into a solar panel. Processes like welding, bonding, wiring, soldering, crimp, all those processes are done by skilled manpower. There can be process variations. So all these are controlled by design of experiments, process parameter control, and optimization and qualification. And these are our strong points where we are able to control the behavior of the array that we fabricate and send. The next point is we have a very tight process control. Process quality assurance also works with us so that the process is well in control. We have very high skilled technical and trained manpower. We also make some destructive sequence to ensure that the process is very controlled and processes within our say allowed limits. We always keep to our heritage, and we also always keep to update our systems and update our processes to imbibe the new systems and new things available in the market. The other things that I want to talk is about the testing. Oh, sorry. I think my mic is giving me some trouble. It is out of charge. Okay, I will remove my mic and speak. 1 minute.
Shajilmar?
Yes, ma'am. Hello, yes, sir.
Take care. Take care. Take care.
Okay.
Wonderful. Please take care.
Can I get another? This is.
Yes, ma'am. Some sound problem has come, ma'am.
Okay, let me try my.
The same thing happened at the beginning. We noticed that. I think that's because of that of your Bluetooth mechanism, ma'am.
Just a minute. I'm trying to connect my.
Okay, ma'am. Okay, ma'am. No problem. No problem. Ma'am, please check your. No, it's also 50% sound is there, ma'am.
I think I'm not audible.
Okay, that will
once again,
that can be rectified. Okay, ma'am. I think that's the same problem. We have cleared it at the beginning.
Shall I remove this and try?
I think it's good to remove these earplugs and speak directly to the lab. I think that's better, ma'am.
Okay. Am I audible now?
Yeah, clearly audible, clearly.
Okay. So I have tried to put another Bluetooth device.
Maybe some battery charge problem may arise, ma'am. That's it.
Yeah. So is okay. I'll come back to my presentation. I'll continue. Okay.
Please,
Next,
please. Okay, ma'am. Okay, ma'am.
Yeah. The next activity which I want to highlight is our testing methods. We have so many NDT tools that we have installed in our system, like sun simulators, then for crack detection, electroluminescence inspection methods, scanning acoustic microscopy to ensure that the welding is proper. So many NDT tools are installed, which helps us in ensuring the quality of the hardware that we design during the design phase as well as in the flight phase. So these NDT tools are exhaustively used for controlling our processes. Another aspect is the qualification test. The qualification test we run very enormous qualification test we do to study and prove that our systems pass as well as live more than the requirement which is ensured by the mission or required by the mission. We also have a philosophy of test as you fly. This is a very tough lesson that we learned. We make some small coupons and test hardware, and we test it, and it will not be identical to our flight hardware. So sometimes we have seen some failures in space in flight, which is due to the small changes that we have incorporated with respect to the test hardware which got qualified or life tested. So now we are testing the hardware in an identical fashion as it is flying. So this also has helped us in identifying and removing the small incidences which can be avoided or improved upon as we make our flight hardware. In addition to that, we perform very detailed acceptance test for our incoming material, and also we verify the performance of the hardware that we realize for flight. So these are the major 4 quality control measures that goes into the realization of the flight solar panel. I'm really sorry. I wanted to include so many photographs, but I wanted to keep the lesson to a younger audience. That is why I did not go too much into the technicalities of this. But I will give my personal, mail ID, so anybody can subsequently contact me if anybody is interested. Now I will just talk about the types of space solar arrays that are prevalent as well as flown in space. This is the model of our first satellite launched by India, Aryabhata, in which we have used body mounted solar cells. You can see the full structure is covered with solar cells, and as and when the spacecraft spins or whichever phase sees sun, that phase will be generating power, and this kind of configuration is called body mounted solar panel. This is not very much preferred now, because satellites are very small satellites only are spinning satellites. All other satellites are 3-axis stabilized, or they see the different parts of the space without spinning much, and more number of solar cells need not be populated like in this configuration. So we have moved from body mounted to rigid deployable solar arrays, which is shown in the second picture. This kind of solar array we have made for many of our satellites launched by ISRO. Here the solar arrays are made in different solar panels, and they are assembled into wing, which gets stowed to the satellite body during launch and deployed once it is going to the orbit. The third kind of solar panel which is used very much in the world, this is the umbrella kind of ultraflex fold out solar array used in the Mars mission by NASA. Here the individual solar panels are rigid, or the panels need not flex, but they are folded in such a way, like an umbrella is folded, so that the stowed volume is very small. This is called fold out or flexible fold out solar panel. This is a very advanced solar array which is used in international space stations, and probably in our future missions also we may use similar fold out arrays, where the solar cells, its substrate or the structure as well as the glasses, everything is made foldable, or they are made flexible, and the solar array is rolled as a what do we call around the cylinder. The solar array is folded during the launch, and once it is to be deployed, it is deployed in such a long spindle, and this kind of solar array is called rollout solar array. So these are all the major solar arrays which are being used in the industry, and which are probably as the person who introduced, they were talking about the space solar power some time back. Maybe in future we may be making this kind of rollout solar arrays which can support the power generation in space and power usage or transmission of power to earth and usage in earth. That kind of missions probably we may be using the rollout solar array. So I think, yeah, I could finish this lecture in 1 hour and 15 minutes. And I thank the audience who have been very patient. And now I think our question and answers session can start.
Okay, thank you, Krishna Priya ma'am, because your kind consideration to our young students who are the beginners. We could say that they are students from even first standard sitting here, and you arrange this content in that manner, in such a hierarchical and gradual level you kept, and we could see the evolution of all these things and the development of these solar arrays. And that included the very low end, you started from the very beginning, from the foundation itself, and it was gradually going on. Because it's also applicable for me. I am a person with from a zoology background, and I could remember the things I learned in my high schools and even the pre-college days. I think that's the case of the students also sitting there. Very interesting, and it has its own flow, and we could understand it well, even though that the content is a little bit tough for the beginners. So it was a really wonderful presentation you have done here, and also we could see that you are in a research mind. You are also a research scholar, I think so, and you are ongoing your research on this aspect also. We expect few more contribution from your part to the great organization of ISRO, ma'am, and we will be ever thankful. And before we go into the question and answer session, we will get some more reflection. First, I invite the founder of this US Space Club, E.K. Kutty sir, our honorable E.K. Kutty sir, to make his own reflection on this class, on this presentation. Welcome, sir.
Thank you, Sajal Mash. It has been a long-awaited talk. In fact, the director of URSSC, Mr. Krishna, ever since he nominated you, Priya Madam, we have been awaiting to listen to you. And it's a very, very worth waiting talk. And we already had Nandini Harinath from URSC, Murali NS, Subramanya Abi, and now you are there. Of course, there is.
So many of
I'm coming to that. I'm coming to that actually. So they all spoke, and this is becoming an excellent forum where a lot of attraction is happening to ISRO veterans to come and listen to you people. Now, as you said, I find you will find here Dr. C.M. Nagrani from SAC. He was sitting in our crowd. PJ Bhatt, Papan, C.S. Prasad. I saw him for the first time perhaps. Rajanga was here. V. Mahadevan, last time also is there. T.K. Sundaramurthy is always there. And it's a very, very excellent occasion where students are mixing with veterans and then listening. And then they are able to get across the senior people later. In fact, some of our students, people like student like Sriram, who spoke in the beginning, etc., they are so excited to get into the fold of these veterans, and they feel that they are at ease to contact them, talk to them, and get more about what they want to know. In fact, they're quenching their thirst is happening in a very, very nice way in this webinar process. So it's a very nice thing, and with all these things, their confidence is going up. In fact, the students themselves are coming out with new ideas. They have already fructified an idea of a magazine. They have brought out a Stellar Chronicle. The first issue has come out, and it is there in our website, UL Space Club website. It is very well commended by very senior people and students as well. And and now they are contemplating, they have big dreams, like what Kalam's dreams kind of thing. They want to build a satellite also. I don't know whether we have a wherewithal to do it and to go ahead, but we don't want to discourage them. We are asking them, you study it, and they are in a study phase now. So these are the kind of students we have, and your presence has made them much lighter in their quest for knowledge, and they feel their confidence is going up. And thank you very much. So nice of you that we have a program like this. 23rd May 2020, we first had our webinar, and now we have just crossed 1 year. So 37 regular sessions we had, in addition to another 10 or 12 special sessions, etc., like Moon Day kind of things, Kalam's memorial and things like that. So a lot of things we had it. So these are all made possible by people like you, Krishna Priya Madam. So also the veterans who are sitting here, and we get lots and lots of support with them. Today, a few regulars are missing here, but yet, it's been a very, very nice thing. I don't know many other people. I think your friends, Krishna Priya Madam's, a lot of friends are here, and two of your friends raised very apt questions. Anyway, we will have an occasion now itself. I will not come in the way of the interaction with you. I will close now itself, and let us begin that. Let them come to the forum and raise that question so that can be shared by all of us here. So thank you very much, Krishna Priya. We'll be in touch with you, and thanks very much to you and your director who made it possible. In fact, today morning I had a talk with him. He remembered. He told me that today there is a talk by Krishna Priya. Kunya Krishna himself remembered, and he told me about it. So I'm so happy that it is being followed up so well. Thank you very much, Papan. Rajangam is still there. Hello, Rajangam. So all these veterans sitting here is, I feel so proud.
Hello. I'm just listening.
In the midst of,
I'm just listening.
Thank you, Rajangam. Thank you.
Thank you, good sir. And we want to get some more reflections before we go to the questions sessions. I invite Padmanabhan sir. He's continuously supporting. He's nurturing our speech.
Okay, Rajangam.
Yes, sir.
Rajangam, please. Rajangam, your mic is off.
You are not audible, sir.
No, please continue. No problem.
Okay, now it's okay. Now it's okay.
Krishna Priya, very well spoken. That's all the point.
Thank you very much, sir. Thank you.
That's all, Rajangam. Anything more?
Hello. Can you hear me now?
Anything more? Your comments.
I just want to compliment Krishna Priya for the excellent talk she provided. Okay, thanks a lot. I told Anil. And that's all.
Okay,
you can continue.
Okay, Padmanabhan sir.
Papan.
Sir,
I told you, compliment is much better, no?
Please unmute the mic.
Very nice.
Thank you. First of all,
Well organized.
A well-organized and a well-executed talk, I should say. From the energy equation, fundamental physics, to the complex process of making a solar cell to fly in the satellite and operate. That's all. I should say that. Wonderfully done. And it's a very good lecture for the students also. Thank you, Krishna Priya. We have not met. Maybe because I left before you joined.
I joined in 97.
I left in 95.
Thank you very much, sir. And we want to hear words from PJ Bhatt sir. He's also Bhatt sir, please.
Anyway, I think we will spare time for question answers. I just want to tell one thing. Krishna Priya, thank you so much. I learned good amount of it today about the solar cells and solar array. Even though I have worked, my field was something different. But I was 100% sure this is going to be one talk. Every one of these talks arranged by Kurti sir and with the help of Kunni Krishnan, I think it is making me enrich my knowledge on various aspects of satellite technology today. And thank you so much, Krishna Priya. It was a very, very excellent, comprehensive talk. Thank you.
Mahadevan, are you there? Mahadevan, are you there?
Hello.
Please give a comment. Please.
Yeah, this was an excellent talk on solar cells and arrays together. And solar cells also, right, from student point of view, she explained so beautifully the physics part which they need to take into account while doing it. At the same time, she also went through very systematically from the cell part to the space qualified ones and also to the terrestrial ones which are being used. So she covered a very good area, and it's a great thing. And then also the aspect of fabrication, process, and the qualification. This is such a big job which people in the job will know it, and that also has been very well explained. So it's a absolutely fantastic lecture and very useful for students and researchers. Thank you very much.
Sundaramurthy, are you there? TK Sundaramurthy?
Yes, sir. Yes, sir.
One word, please.
Oh, I think, sir, I don't want to stand in between the students' interesting question. I'm waiting for their questions. In fact, we are learning much more than what we have learned from our experience from these students' question. Anyway, but congratulations to Krishna Priya. You have aptly covered the subject from the beginning till that various types of solar panels used in this space program. So that I think it was nicely summarized. It was a very good understanding for us also. I think I can say it was an adult education for the people who are not in that system. Thank you so much. All the best for you.
Thank you, Sundarimurthy sir. And I could see.
CS Prasad, are you there? CS Prasad, the one last attempt from veterans. CS Prasad, I think he seemed to have left.
Sir,
Okay,
sir,
go ahead.
before we concluding these reflections, I could see one raised hand from Joshi sir, ISRO, and he raised his hand first, sir. Okay.
Okay, am I audible?
Yes, sir.
Okay, this is Jagannatha, formerly a CMD man. I am extremely happy because since 2011, I'm an alumni of International Space University. Krishna Priya Ganesan, I must compliment you. This is how Professor Dhawan used to give presentation, one of my mentor. Now, after becoming alumni at International Space University, since 2012 COSPAR, I'm regularly attending COSPAR and IAF. I want to mention to you one thing. You missed one point, that is keeping at a geostationary orbit, a reflector-like thing, which could feed the energy requirement of the world. Because my PhD now is on climate resilient. So the options, and for example, in Bangladesh, the poorest of the poor use the solar power to earn 15,000 rupees. They don't have a legalized resident. See, climate change and your presentation are linked. What I liked is yours was such a wonderful basic thing. It's like a primer. It's like a primer for energy students, whether it's first standard or as our Sundaramurthy sir told, whether it is first standard solar energy or energy student or to the most advanced and also another thing, last thing I would like to tell you, in missions like Mars mission, we don't go for the solar panels. We use the nuclear fuel for various reasons. At some point of time, you can keep it as a future research prospect. Thank you very much. Wish you all the best. Thank you.
Thank you, Jagannath sir, for your valuable comment and joining with us. And I invite Joshi sir. He's raised his hand first. Please come, sir.
Yeah, very good evening to all of you, and my compliments to Krishna Priya ji for a very well structured, very well explained, and in a lucid way. It was an excellent presentation. It went like a old Bollywood movie where you take us to some flashback, like from some basics of physics, then you run us through the current technology, the fabrication process, and to the latest state of the art. It was excellent to learn, and I always had a fantasy to know about solar cells and solar array, because this was the only area in my career with ISRO where I did have minimum of knowledge, and that is, I think, today that has been fulfilled. So I am very thankful to you, Krishna Priya ji. Thank you very much.
Thank you, Joshi sir, for your compliments and participation in these things. And next we enter to the next most interesting session of this program, that is questions and sessions. And I invite Navani to deal that session. Okay.
Am I audible?
Yes.
Yes, you are Navneet. You are.
Right.
You are audible.
So, good afternoon to one and all. My name is Navneet Chejil. I'm a member of US Space Club. So, I'm going to deal with the questions. So before we get into the questions that are from students, we do have two people who had asked the questions in between the session, Miss Fahana and Miss Archana Gujar. And I invite you, please post your queries.
Okay, this is Archana. I'm really sorry. I didn't know that I should not disturb in between. So, shall I put my question now?
Yes.
Yes, Archana, please go ahead.
Okay. Ma'am, I had one question. Like you told, this corrosion due to atomic oxygen. So, when we are separating from launch vehicle, so that time also the altitude is very less. So, whether that time also it will affect our solar cells? This is first question.
This atomic oxygen is not a fast moving entity in low Earth orbit. They are just like clouds hanging around, which is at different altitudes. So when the satellite moves at a very high velocity, say a few kilometers, a few thousands of kilometers per second, the satellite ram velocity is what is enabling the atomic oxygen to attack itself. Otherwise, the atomic oxygen is not having enough energy to hit you and damage your surface. And it is not a very short period activity. It happens slowly and a long process. That is why the satellites or the satellite appendages which are exposed for years together, they get slowly eaten away by the atomic oxygen. It is like the corrosion that happens in ground. Like we use silver and other precious metals, it doesn't get corroded in a short time frame of say 1 day or 2 days if you get exposed. But for years together, if you leave a silverware outside, you will see a black coating on top of it. Atomic oxygen also is same way. So the launch vehicle, when it takes the satellite to the orbit, it gets exposed to a very short time, and due to which the attack due to atomic oxygen is not very significant.
Okay, thank you, ma'am. Ma'am, I have one more question. This whatever arcing is happening in the solar panel and geo orbit, how we are taking care and whether it will affect our satellites?
Okay, arcing is happening mainly in satellites which is having a higher bus voltage, because the arc threshold is also affected by the bus voltage that we select. The higher the bus voltage, the probability of the arc to affect the satellite components or our solar array components increases. The way we attack arcing is by doing some 2-3 basic care. Number one is the triple point has to be avoided. That is, that three things has to come together for the arcing to happen in a solar array or a satellite appendage. One is insulator, which can get charged to a very high voltage. The second one is a metal which can take the arc or which can receive the charge which is trying to get settled. And the third is the plasma. So plasma provides a path for the insulator to discharge to the metal. So this triple junction has to be avoided. That is the first thing. The second thing is arcing happens if the two, that is the charged surface and the other surface is very much near to each other, and the current is very high. So all these things we avoid by making sure that the metals in the solar array are protected with dielectric, and by putting dielectric, we are pushing up the arc threshold. This is said that these are all preventive measures. The corrective measure that we or the modeling that we do is we predict how the arcing will happen in our solar array, as well as we test our hardware in an arc facility which is available with BARC or our Institute of Plasma Research in Ahmedabad. So many things we do. One is we take care during the design. Second thing is our design or our hardware gets tested, we get confidence, and subsequently we fly. So that our ISRO satellites so far with 70 volt bus, we have never had a problem so far.
Okay, thank you, ma'am. Ma'am, Farhana here. I think my question also is answered with this explanation. Thank you, ma'am. Thank you for a very nice
You
lecture.
ensure a gap also increase between the in solar layout that is taken care.
Yes, we make sure that the generating part and the insulator, they are moved apart, and also we fill the interface with dielectric so that the arcing is, we cannot prevent it completely, but it is pushed up. We are trying to avoid it.
Okay,
Thank you,
ma'am.
Srinivasan sir.
You are mentioning about IPR, plasma research. ISRO had a role in incubating it in Ahmedabad. PRL was the place where it was born with Dr. Kaur and all that. So this is a lot of linkages with this kind of technologies. Thank you.
Thank you, sir.
So now we can get into the questions that are posed by the students. So here are a few questions that we collected. So the first one is from a US Space Club member. He is one of our peculiar member, since he is only a fifth grader and has a lot of free time.
Can you speak a bit louder?
Is it okay, ma'am?
Yeah.
All right. So the next question is from Adidev A. He is a US Space Club member and especially a peculiar person, since he is only a fifth grader, but shows an extreme interest in space science and devotes a lot of his time into the field. So his question, I would like to start with his question. So his question is that why are most solar panels blue? I remember seeing some orange solar panels.
Okay, I first want to give my what to say, my respects to the person who is in a 5th standard and raising such questions. I will try to answer the question in this way. The solar panel on the top surface is provided with a special coating which makes sure that the light incident on the solar cell is going into the solar cell. Any mirror surface or a polished surface, you would have seen that a part of the light goes inside, but a major part of the light comes out due to reflection. So to avoid reflection, we are giving a specific coating which is called the anti-reflection coating. The anti-reflection coating is made by some oxides of some non-conducting oxides, and the natural frequency of that oxide is what is causing the color of the solar cell, which is mostly blue in color. In silicon cells, you would have seen it is mostly blue in color, and in some other cells, you would see a dark green color. And in the present or later cells, like perovskite cells and all, you could have seen some orangey tint also. So the anti-reflection coating and whatever light it naturally sends out, or it is not taking in, that is what is causing the color of the solar cell.
Yeah, yes,
Krishna Priya madam, I just wanted to say this boy who asked this question is one of the most active boys amongst our UL Space Club. We have got a group called
I'm very much impressed.
We have a group called Cosmos. You have to see the kind of intervention he makes, even at the dead of night, 12, 1 in the night. He will be. I can see him in that active in that. I met this boy when he was in 1st standard. Her mother brought to me this boy when he was 1st standard, and he was at that time, the level of his knowledge and his interest was something I don't know how to describe it. So this boy has made a presentation also when he was in 4th standard. He made a presentation in our webinar. This boy during last moon day time. So that was the kind of things. So we are very, very happy to. There is another boy from Chennai in 5th standard who is also doing something great like this. Otherwise, our boys are mostly 9, 10, and plus.
Sir, I would like to compliment you also, sir, because you are giving so much of support to such youngsters who are getting this opportunity and able to imbibe the knowledge and use that knowledge to increase their knowledge base, as well as they are all inspiration to the other children. So I would like to compliment UL Space, who is making this platform available so that we can also know about such projects.
By chance, I happened to land here and doing it, and not so much of a design. I just happened to meet some students and then found interest in them. Then I fell in their in their spell. That's all, nothing other than that. Okay, go ahead, Navneet. Navneet, please go ahead. Sorry, yeah.
Yeah, yes. Thank you, ma'am. And next, we have a question. It's by Arya Sudhakaran. What are the major differences in working and usage of organic solar cells from the normal one? What is its future potential and challenges in the space technology?
Okay, in organic solar cells, we use what is called the carbon-based polymers. Whereas the solar cells that we use in space are semiconductor based and solid state physics based solar cells. The cells we use are extremely costly because they have to be mined out of earth, processed, purified, made into crystal, and finally made into a special form for us to use. Whereas organic polymers are abundant and they are very much available and cheap. And also in organic solar cells, we use very small quantity, and we the research going on, it is using the nano scale material, which is very like milligrams of material is sufficient to make a very thin and a uniform layer of solar cell. So the organic solar cell, if it is able to become stable, then it will revolutionize the solar cell market, because it will make the material available. It is very much cheap. The processing is very cheap, and it has already reached efficiencies of say 10s and 20s. So that is the main difference. The polymer versus the semiconductor, that is the main difference, and it has a very bright future because it will be able to make the solar cell affordable. That is the main difference it is going to make in future.
All right, ma'am. So the next question is by Akash Vinu. It's what would be the impact of using graphene solar cells?
Pardon? What is the impact of?
What would be the impact of using graphene solar cells?
Docking.
Graphene material.
Graphene material. Oh, okay. Graphene is a material which is a form of carbon, and that is one way it has a very good band gap, which can be used, but we have to have a stable solar cell out of it. So much of research is going on, and we have to come out with a good solar cell by doing much more research.
So all right, ma'am, I think we can ask one last question, because it's already about to be 5. And the question is by Vinayak. The question is that hotspots are one of the main reasons of solar array getting destroyed. Can you suggest some methods to reduce this?
Okay, hotspots are caused because of either you'll know how the solar array is made. It is made with many individual solar cells connected in series and parallel. So when solar cells are connected in series and parallel, it has to conduct the same current, and finally at the end terminal it has to drop the same voltage. If by chance one of the solar cells in the series length, if it is defective due to some reason, or if it is not getting enough sunlight, or if it is partially shadowed, what will happen is in the IV curve, I will go back to my presentation and try to go back to the IV curve. Okay. So this is the IV curve, which is, you are able to see the presentation, right?
Yes.
Okay.
Yes, it is.
So this is the IV curve, and all the solar cells we will try to match to have the same current. Assume that one of the solar cell is getting a lesser current. So its IV curve will get modified something like this. Whatever my cursor moves, that way. Assume that it is getting only 50% of sunlight. So the ISC will come down to 50%, and this will be, that particular cell will be having an IV curve like this. So when you are trying, all other cells are actually working in this range, Imax. So when you try to pump the same current Imax through this partially illuminated cell, it will be trying to conduct in this reverse characteristics. Its reverse characteristics will be something like this in the second quadrant. So when the same current is trying to be pumped through this particular cell will be dropping the power which is in the second quadrant. That power which is generated by other cells getting dropped in this particular partially illuminated cell is the reason for the hotspot. Okay, so to avoid hotspot, we have to make sure that none of the cells are moved to the second quadrant, or all the cells are functioning in the first quadrant. That is between the ISC and VOC, any point is acceptable, but beyond the ISC or the reverse characteristics region, that is not acceptable. So what we generally put is, if the cell is like a multi-junction cell, we try to protect it with a diode in the reverse or parallel to it, which is called a bypass diode. So if this particular cell is not able to conduct this current in the reverse direction, the bypass diode takes that current and the current is bypassed through the bypass diode. Hope I don't have the proper slides and I don't have a blackboard also, so I'm not able to draw and show you. Hope my explanation is satisfactory. Otherwise, I will send you some slides which is explaining this.
All right, ma'am. Thank you so much. And it's already past 5. And I would like to say that I personally, I enjoyed your presentation very much. And I'm actually just being promoted to 11th. But a lot of things were new to me, but the general content was clear to me, and it was really it was wonderful. So thank you, ma'am. We look forward for your cooperations in the future too. Thank you.
Thank you very much.
Okay. Thank you, Navneet. And
Share, sir. Just one, sir.
Yes. Then I am going to. Then I invite Varun. He has to make some more declarations here. He's a major brain behind this mechanism, and he's united these things, and we are following him. And Varun has to say something more about the UL space today and some other things.
As our usual sessions, today also we have a quiz which is connected to this topic of our webinar session. We'll have a quiz on solar arrays and cells and overview. So this is the topic of today's quiz, and we are posting the quiz link of our Google form for this UL Space Club quiz session 37 in the chat window. You can access the quiz only after the vote of thanks of this session. The quiz will close on 7 p.m. Please do it as fast as possible. The quicker and accurate answer will consider as the winner. So all the best for all of you. Please try to attend the quiz. There will be a prize, which will be a voucher of a book. That's what we are doing for the winners. So please try to attend the quiz, and all the best for once again. Thank you, sir.
Okay. Thank you, Varun. And Varun is an engineering student, and he's also sowed the seeds of some dreams in our students to make a satellite also. He's thinking like that. And I invite Kuti sir to declare about the future upcoming events.
Okay, nothing. Next event is on 3rd July. A talk. Normally we do it on 2nd Saturday, but this time we are fortunate to get an IIT professor, and she is available only not available on 2nd Saturday. So she agreed for 3rd of July. That is another Saturday, 1st Saturday of July. Dr. Preeti, she is assistant professor, a young lady, very young lady, assistant professor IIT Bombay, and her topic is machine learning. What is it and why should we care? Machine learning, what is it and why should we care? So this is the topic. She is a artificial intelligence area AI professor, and I'm sure it is going to be an exciting talk. So that is our next program, next webinar program. Varun, you have anything to say about your own program for the Moon Day?
Yes, sir.
Internal program?
Yes, sir. Moon Day program, we will have competition as I announced in the first part of our webinar. And more than that, we have a team named as Team Gravitons, which is a team under UL Space Club, led by the student fellows of UL Space Club. And we are doing a workshop series on satellite technology. And our respected Sundaramurthy sir will have interaction with our students tomorrow 10 a.m. So we are very happy to have Sundaramurthy sir on that session. If anyone is interested in the talk, I can give you the details of the talk, and you can contact through our mail ID. So that's about it, sir. And our competitions, Moon Day competition registration will start on 20th June. The registration will be available through our website. UL Space Club have a website, and like Kutisa already said in his talk, the website link has been posted in our chat window. Please visit our website for more details. That's a good, sir.
Okay, thank you, Varun. You are creating such a wonderful environment for our students, and they are flourishing there. We are so happy to see that, and we can proudly say that we are not only convening these kind of monthly webinar. The whole students are working the whole 30 days in a month, and they are thinking about it, and they are exploring it well. That's why there is a lot of discussion, debates, and organizing things already doing there. And we have a quarterly magazine with us, Stellar Chronicle, and chief editor of that Stellar Chronicle is with us. Jairam sir is there. I invite Jairam sir to say. Jairam sir. Varun, I couldn't see him here. Jairam sir, are you here?
He was there a little while ago. He was there.
He
I
was
think he left.
there. And, okay.
He was there. I think he left.
Okay, that will happen. He's organizing these things. A group of students are doing that. Okay, sir. Okay, sir. Then we'll hear him. And all the activities are now published in our website, uspaceclub.in. And the 37 webinar we already conducted. All these things are, the YouTube link is given there, and that's available. And the upcoming events also will be published through our website. We can proudly say that. And now we are going to the concluding sessions. I invite T. Damodaran sir, who is the convener of the Vagabhananda Edu project, is working under the Uttarangal Labour Contract Society, is a major cooperative sector service infrastructure building organization. The bigger cooperative sector movement in Kerala or in India is representing ULCCs. I invite T. Damodaran sir to make vote of thanks on behalf of UL Space. Welcome, sir.
Hello.
Yes, sir.
Am I audible?
Yes,
sir.
you are.
Yes,
You
sir.
are. Go ahead. You are audible.
Thank you. Thank you. Good afternoon, everybody. First of all, I thank all the distinguished persons joined in this webinar conducted by UL Space Club, run under the umbrella of ULCCS Foundation. Subject of today's webinar is of great importance and very relevant. For future energy, we are looking the sun for its abundant energy. Every day, even today, we are trying to use solar energy in every walks of our life. Governments are proposing and to impart the solar energy so many facilities to go for alternative energy sources instead of conventional energy sources. Maybe after some years, house lit with solar cells and appliances. Now we are on the lowest step of this technology. In this context, the subject of this webinar is very useful. Krishna Priya Madam has described vividly and systematically how the cells are arrayed in the satellites and well responded to the questions. So I thank Krishna Priya for giving us a very useful and knowledgeable speech. In this occasion, I am proud to thank you on behalf of ULCCS Foundation. The talk was well organized and interesting. The students, I think the students were waiting for such a talk in a webinar organizing by UL Space Club. I extend my sincere thanks to all the veterans for participating in this webinar and thanks for making comments on the talk. I must thank the participants who made this program very interesting and meaningful by asking questions. Then I thank E.K. Kutisar, who is the backbone of US Space Club, and our other organizers like UK Shajil Master, Varun, Navaneet, Sriram, Adil Krishna, etc. for making this program very successful. Then I thank all the students and others who participate in this webinar. Once more, I thank all and I would end my words. Okay, thank you.
So a very nice day has come to a close. Okay, today is INSAT 1D anniversary, isn't it, Badsap? I saw your posting, about it and all that. It's a very nice day, very nice day. I think the satellite in that series which worked very well. It is very nice. Thank you very much, Krishna Priya Madam. You must be tired. You have spent a lot of your energy and time in satisfying our student. Thank you so much. I think we will be in touch. Kindly help us